Okay, so this is the third part of the video where we go over how we can evaluate the predictive ability of our logistic regression model. So in the previous part, we kind of just went over in detail, right, the terminology associated with a confusion matrix. And really the key measures that I think that we usually are concerned with will be accuracy or the error rate. So the error rate will be 1 minus the accuracy, but also the false positive rate and the false negative rate. And I've kind of mentioned that depending on your situation, you might want to reduce, right, either the false positive rate or false negative rate by adjusting the threshold. But bearing in mind, right, that if you adjust the threshold to reduce one of these errors, then the other error will increase. So that will be a decision that's really driven by the kind of problem that you're working on, right? Which error is more consequential. So what we're going to talk about next is just some ways to summarize the ability of our logistic regression model, right? So we talked about confusion matrix. Next, we'll talk about what some people use, the ROC curve. So ROC is short for receiver operating characteristic, and its original use was during World War II when people were trying to analyze radar signals and to distinguish, right, signals due to enemy aircraft from signals due to, random noise such as a flock of birds, right? So you might think, right, what's the more crucial error, right? So if it's truly a flock of birds, but you think it's an enemy aircraft, you might fire something at the birds. But the flip side would be, right, if it's truly an aircraft and you think that it's a flock of birds, you do nothing and your base gets bombed. So, right, as I said, different kind of errors, right? So you might have to change the threshold depending on which one's more crucial. But what's an ROC curve? It's a two-dimensional plot. Sensitivity on the y-axis, so as a recollection, sensitivity is, right, classifying that person as a success, where when that person is truly a success, and the false positive rate, or 1 minus specificity on the x-axis. So 1 minus specificity, right, is given by this, but notationally it's given by y hat equals 1, given that y is truly 0. So some people call the sensitivity as true positive rate. I might have failed to mention that. So that's what the ROC curve does, right? It's a two-dimensional plot, sensitivity on the y-axis, and false positive rate on the x-axis. Now the ROC curve will then plot the values on the sensitivity and false positive rate for every possible value of the threshold. So what it does is that it will vary the value of the threshold from 0 to 1, right? And for each value of the threshold, right, they will create a plot. So maybe when the threshold is 0, right, the value will be over there, right? When the threshold is 0.1, right, the combination of sensitivity and false positive rate could be that, and then, right, for a different value. So we keep creating all these plots for different values of the threshold. And then they'll try to, like, put a nice curve on it to kind of summarize it. So the ROC curve, as I said, summarizes the combination of true positive rate and false positive rate for every possible value of the threshold you could use. A model that classifies at random, that means it doesn't use any information from the predictors at all, will have an ROC curve that lies on the diagonal, right? So basically, right, if you look at the ROC curve, a model that guesses at random will lie on the diagonal. A model that classifies all observations correctly will have a sensitivity of 1 and specificity of 1 as well, right? So remember that the y-axis is sensitivity and the x-axis is 1 minus the specificity, right? So if sensitivity and specificity is at 1, that means a model that does perfect classification will be at the 0, 1 point over there. So the idea is that if your curve is closer to this point, gets closer and closer to this point than the diagonal, right, then your model does better than random guessing. A model that classifies all incorrectly will have a sensitivity and specificity of 0. So that means its sensitivity will be 0 and 1 minus specificity will be 1, right? So the wrong one will be over there. So the idea is if your curve is on the other side of this diagonal line, right, that's closer to this point over here, then your model does worse than random guessing. Okay, so what I'm going to do next is explain a little bit more about why this first statement is true, that a model that guesses at random will have an ROC curve that lies on the diagonal. So I'm gonna just talk about a few properties first, right? So this is something you might have seen in your probability class, right? So if events A and B are independent, that means they don't influence each other, then the probability of A happening given that B has happened will be the same as the probability that A happens given that B did not happen, so that's B complement. And basically these will be equal to the probability of A happening. So basically we are saying, right, probability of A does not, the value, the probability does not depend on whether B happened or not. Right, so this is what we mean by events are independent. So let's consider the model that we say guesses at random. Right, that means the info provided to the model doesn't help. Right, so that means if that's the situation that you have, what this implies is the following: that the probability of getting classified as a 1 given the data at hand is equal to the probability of being classified as 1 given that you have different data. Right? Because if the data doesn't help, that means these two probabilities are going to be the same. This implies that the probability that you're classified as 1 given that you're truly a 1, right, because this is part of your data, is equal to the probability that you're going to be classified as 1 given that you are truly a 0. And we are basically saying that these two values are the same, right? Now, and this basically tells us, right, that they are independent. So this left-hand side here though, right, this first term is the sensitivity. And this term over here on the right is 1 minus the specificity, right, which is also the false positive rate. So this tells us, right, that a model that guesses at random will have sensitivity equal to false positive rate. And the ROC curve, right, does indeed plot the sensitivity and the false positive rate, right? So we are saying that these two are equal, then we are having a diagonal line, right, which is basically like a y equals x. So this is the reason why the diagonal represents the model that guesses at random, i.e. it doesn't use any info from the data itself, right? The classification will always be the same regardless of the true value of the data points. So this is the ROC curve for the Titanic data set, right? So again, as I said, so this data point will represent, right, that at this particular threshold, the true positive rate is about 60% and the false positive rate is about, 10%. Now the one gripe that I have though is that the ROC curve doesn't tell you, like, so I just read off this point, but I have no idea what the threshold is that corresponds to this point. Right, I just know it's a threshold from 0 to 1, but I don't know what exact value. Right, what is the threshold at this combination of true and false positive rate? I don't know. So that's kind of one of my gripes about more standard ROC curves, that it's hard to get that info. So another way to measure the classification ability of the model is using the area under the curve. It's basically, again, it's based on your ROC curve. So again, you have your sensitivity and 1 minus specificity over here. And it basically say, if that's your ROC curve, we're just trying to find then, let's say we integrate the area under the curve, and what is that value? So remember that the values, right, for the ROC curve goes from 0 to 1 on both axes. So if you have the model that guesses at random, right, it's basically this diagonal line. So the area of this triangle, right, is going to be half, right, because right, from your high school days, that's the area of the triangle. So for a model that guesses randomly, your AUC will be half. And if your model does a good job, right, the perfect model is an ROC curve that will look like this, right, where it's close to that point. So this is basically like a square with area of 1. So an AUC of 1 indicates a model that classifies everything correctly, right? So the closer your AUC is to 1, the better it is, right? And the closer it is to 0, that means it's worse than random guessing. And the AUC in our example is about 0.8184. Again, it's a summary, right, for all possible values of your threshold. Now, okay, so right, we talked about the ROC curve and the AUC. I'm going to mention a few things about some things to be careful with, right, when using the ROC curve, AUC, and maybe some of these measures that we talked about. So the measure of accuracy can be misleading, can be a misleading measure, especially when you have unbalanced sample sizes of the two classes. So that means that, right, the number of people that are truly yes and truly no are very different. You can have high accuracy, yet you could either have high false positive or high false negative rates to be really high. So what do I mean by this? Let's consider this situation. So let's say we have a useless model, classifies everyone as a 1. And if you look at your confusion matrix, this is the resulting confusion matrix that reflects this scenario. That nobody gets classified as a 0, so this first column will be blank, will be 0, and you only have 50 people that were truly 0, and you have, say, 5,000 people, right? So this is an example of unbalanced data because you have 5,000 people who are truly 1 and only 50 who are truly 0. But all of them with this useless model will be classified as a 1, right? So you can kind of see in this situation, the accuracy of this model is going to be 50 over the total sample size, right? So this is less than 10%, but in this case, the false positive rate, right, which is probability that your y hat equals 1, given that y equals 0, right, is going to be 50 out of 50, which is 1. And the false negative rate, in this case, will be 0. Right, so if you just look at accuracy, you might not, without looking at the confusion matrix, you might have this false sense of security that your model is doing a good job. Right, but once you look at the confusion matrix, calculate the false positive rates, false negative rate, you kind of realize something's going on. So this is an example where, as I say, so accuracy can be misleading, especially when you have unbalanced sample sizes. So just be aware of this over here. So let's go back this. Right, so in this situation, it's more informative to look at the false positive, false negative rates, as well as the confusion matrix. One thing I'll also mention is the ROC curve shows the true positive and false positive rates as the threshold is varied. It does not immediately inform you of the true positive and false positive rates for your specific threshold that you use. Right, so you could have an ROC curve, right, so that's the diagonal, and that looks pretty good, but you don't know, right, for your specific threshold that you're thinking of using, maybe you're over here. So if you're over here, you're on this part of the ROC curve, which is on the diagonal. So you're not doing any better than random guessing. Now, if you know that for your specific threshold, you're actually there, then you're pretty confident that your model with your specific threshold is doing a good job. So the ROC curve does not do that. So looking at the ROC curve on its own could give you a false sense of security as well, because you have no idea if your specific threshold results in that value over there on the ROC curve. Right, so it does not give you information about your specific threshold. AUC, just as like the ROC, is a summary of the predictive performance for all possible values of the threshold. It does not inform you of the ability of based on your specific threshold. So just be aware, right, that these are summary measures, but they do not address your specific threshold.